Hey, what's going on, folks? It's Mike here, and by now you know the drill. This is our first impression series, and today we're going to be looking at a fun language called OCaml. Fun because it's known as a functional language, and our first of the functional languages that we're going to be talking about in this series here. So before we dive into OCaml, let's go ahead and take a quick look at the Wikipedia page to learn a little bit about it, its history, and then we'll go ahead and get set up and just do a brief tour of the language in 1 hour or so. So OCaml, as I understand it, and I have used it again in limited capacity. I used ML, which is a sort of variant of OCaml in a programming languages course long ago here. But what's kind of neat about OCaml is it's a multi-paradigm language. It's primarily known as a functional style language. So again, we're going to be doing some things a little bit differently here, but it does have imperative style and object-oriented support as well. So that makes it kind of interesting because you kind of think if there's going to be a functional language that really takes off, maybe this is an entry point. I know a lot of folks who have used this as entry points. I know it's been used at places like Facebook or Meta, for instance. Jane Street, another sort of famous example of using the OCaml language. So anyways, kind of makes it interesting language, and by, programming language standards, it's relatively modern, came out in the 90s here when this was developed. So they had a lot of time to think about and get inspired from other functional programming languages in that sense here. Now, OCaml has had some influence here, I'll say, by INRIA, which is over in France, and is a pretty high-powered research institution, and has done a lot of great stuff as far as I know as a sort of bystander in the programming languages world. So it's kind of interesting there to see how it is. Again, it's an ML sort of derived language there. Again, known for static type systems and type inferring compilers. So there should be some cool stuff. But with that said, let's go ahead and just look at the OCaml webpage. Let's see how it sells itself. And then we'll go ahead and try to download it and learn with OCaml. In fact, let's keep some of these tabs open. But let's dive into the actual language here. So I'll go ahead and get the install going here. Let's just go ahead and set that up in another tab here so we don't lose any time. It looks like there is a package manager, which we've seen in some of our other languages there. That's a good thing. So the OCaml package manager, OPAM, I guess maybe it's pronounced, I don't know here. Okay, it installs the compiler as well as any additional packages. Okay. Let's actually just get that going here. As I said, I don't want to waste too much time here. Where should it be installed? Yep, that's fine here. I'm going to put in my super secret password. And let's see. Oh, was that it? If I type in OPAM or something? Okay. OCaml? Interesting. Okay, well, we'll figure out how to install this here. Okay, so we need to initialize. Okay, we'll take a look here. Let's see. OCaml init. Okay, so it is starting up some process here to get us set up here. So let's go ahead and that's it. We'll have OCaml at that point here, and then there's a switch that we can set up here, and we can just execute commands. Okay, neat. Oh, and there's a whole set of tools here. Okay. Okay, let's go ahead and do this as well. Okay, let's say yes to everything. And let's continue our little tour here. So anyways, again, these aren't necessarily tutorials. Maybe you'll find something better here, but my first impressions here. Okay, I mean, pretty clean language here. It is a functional programming language here. And I mean, this is the beauty here, right? You get to use some of your recursion. This is the stuff I remember from ML, let, this is gonna be a recursive function here, x equals, and then, it's very, very concise, these functional programming languages, right? They're highly expressive. You're just sort of thinking about the computation you want to do. And here is the recursive part, and of course here's the base case, right, if we're less than 1, and then otherwise the recursive part here. I mean, this is pretty much the same as any language here. What's sort of interesting as far as the function calls, which might be new for us as we looked at a lot of C-based or curly-based languages, right, no parentheses here, okay? And after the result here, you can see the actual type that's produced here, okay? So that's kind of interesting here. All right. As I mentioned, in the programming languages world, which is, SIGPlan, the special interest group on programming languages, it has been, recognized with a special award here. Okay, so it has been used. And here are some more of these places, that have used OCaml. Again, famously, Jane Street's the one that folks I remember always talking about. Somewhere I have a deck of cards from a programming languages conference from those folks, but Facebook or Meta, Microsoft. I'm sure a lot of folks at other companies, I mean, this is kind of true of any programming language, maybe use this to build command line tools or other, small programs or something. But, these companies, some of them, again, famously, Jane Street, like this is part of their infrastructure. As far as I know, I haven't worked there. Okay, so let's see. It's known for its highly expressive type system. Okay, catching bugs at compile time. And this is where, a lot of programming languages these days are trying to push computation towards compile time. Again, you see me use dlang a lot. There's a lot of interesting stuff we can do at compile time, which is interesting. But again, with a strong type system, or again, languages like Rust, right? What bugs can you detect at compile time? That's the best time before they even get to the user or you as the developer who has to iterate and find these things. All right, so that's with their type system, and it looks like, okay, is it garbage collected? Okay, so you don't have to really worry about memory management. Again, I'm a fan of garbage collection. I like systems languages that have garbage collectors. Makes my life easy, and I can still, try to get performance. So systems at scale, that can be useful. Now, again, it always depends, right? I'm not going to compare languages too much, rather reference languages, but, depends on what you need here. So that's kind of cool. Safety and security, big part of it. Big tooling here. We'll probably do everything in Vim, or if we get to Vim, we might just be on the tour. Now this is kind of cool here. Fast compiler. Okay, bytecode compiler generates small and highly portable executables. I wonder what platforms it supports. I'm assuming, at least Windows, Linux, and Mac, but I wonder if they have stuff on like Android or iOS. Those would be good things to learn from you folks here. All right, and of course, still a very active project, right? This is about a month. I'm recording this, mid-October. Okay, so they've got, SIGWin support, all sorts of good stuff. New data structures coming in. I mean, always good to see things here. And good ecosystem, tooling, it looks like, web framework, scientific computing. Let's take a quick look at some of these here. Dune, I keep seeing this show up here. This is a build system. Okay, cool. It looks pretty simple enough here. It's kind of neat to look at some of these things in other programming languages, because then, even if you have a favorite programming language, you might say, hey, we need that for our ecosystem. Okay, so some scientific computing stuff. Oh, cool. I mean, there's a couple books here. Again, I like seeing books with languages because then I can learn from them. Okay, so educators. So strong ties as mentioned, from India University. And of course, industrial uses. Okay, so we got a lot of stuff here. Maybe we'll open up some exercises here. What do we got here? Oh, wow, this is brave here. We could do something like advanced here. Okay, well, let's take a tour. Let's try to learn the language here. Let's see if our install finished here. I think this is the last thing I need to run here. And then we'll try, see what's going on. Okay, so this is installing Dune, our build system we just learned about, and some of those other popular tools. Okay, that's neat. And a language server protocol, so we could, use this and, our favorite IDEs. Okay, so it's got the tooling stuff. Okay. It's got let's take a look at the standard library here. Always good to see a good standard library, meaning that, some of these things you want to be able to just be able to grab. Now I see something for semaphores, for concurrent programming. That's something I actually be curious with playing around with, right? Functional languages are known for being very pure and trying to not have, so many state changes, which is a great thing for concurrency, right? If your defaults are, everything's read-only, then you can pass data around relatively freely. So it's got locks here. I wonder if it has coroutines. It's callbacks. I mean, there must be some of this stuff either in a library, but I just wonder if it's built in. Or maybe they call them, do they call them fibers or something? Sometimes there's just different names for these things. Coroutine, fiber, no. Let's see, maybe a thread. Okay, lightweight threads. Yeah, interesting. Okay, maybe we'll run into stuff. Oh, this is kind of interesting. Runtime support for lazy values. Yeah, lazy evaluation, another one of these things that I associate with functional languages, right? Don't do the work until you actually need it. And again, that can be a good thing for performance or concurrency as well. So maybe let's just start with the tour here. Okay, so it's telling us to install here, and then we'll write our first program here. Okay, we need to have it installed. We don't need any functional programming language, okay, but we do know about some software stuff, or at least a tiny bit. Okay, oh cool, and they're gonna show us how to use like their pattern matching, call functions, and so on. Yeah, I feel like we should just write our first program here. Oh, now let me make sure I didn't miss anything. Okay, they're showing us some basics here. Well, let's see if we can get OCaml up and running here. Okay, just by typing out some simple things here. Okay, and how do I run this here? OCaml. Oh, I guess there's an interpreter too. Let me go back to those directions. I think I missed a environment variable. Let's see here. Install. Okay. Okay. You need to activate the OPAM switch. Okay, one of these two ways here. Okay, let's see if we can do that here. Okay. And then I can do OPAM execute and then a command here. Okay, so I can do that one of two ways. Okay. Okay, let's keep exploring around here. I gotta figure out how to run this thing here. Okay, let's see. I found another help page here on installing OCaml. Again, just trying to do this as I figure it out here. We are on Linux. Okay. Here's our platform tools. I think I installed those. I ran this. Maybe I need to run it again. Let's see here. But UTOP. Okay, that's our modern interactive REPL. Okay, that's what we want to play around with and try some of these exercises with. Okay, let me make sure I installed everything. Maybe I didn't hit yes to something. Okay, already installed. UTOP. Okay. Oh, wow. Okay, this is fancy. How do we get help in here? What if I do H? Function? Oh, interesting. Semicolon? Uh-oh. What did I have done? Control C. Let's see. And how do I quit this? Q. Exit. Okay, it looks like a command here. Wow, how to escape. I guess we will have to learn OCaml no matter what. Okay, I'm sure the tour will tell us. Let's get into some of these exercises here. Okay, well, let's just type in some stuff here. Now this is really neat. If this is like telling us what my commands are, I mean, it's just starting off here like B, C, D. Okay, I really like that. That's a cool REPL. Again, this is why I'm doing these sort of exercises. I learned so much stuff here. 50 times 50. 2 semicolons. That's right. Okay, now my memory is working. Okay, and that gives us an integer. Yeah, so it's always telling us the type. I mean, this is how strong the type system is here. Yeah, everything has a value, everything has a type. Okay, that's kind of cool. Not a misexpression. Okay, we haven't assigned anything. Let's do 6.28. Double semicolon, that's float. Strings are built in. Hello. Oh, interesting. Here. Unbound value string. Okay, what does that mean here? What have I done? Let's try that again. String equals, this is really disco. And then 2 semicolons. Oh, I see. Interesting. That wasn't a assignment. I need to do like let. Here we go. Okay, and then if I just type out string, yep, we get it back here. Okay, cool. Looking ahead here. Okay. OCaml has type inference. Okay. So I like this. And this is something, you know, we're seeing in a lot of modern languages with auto, D, C++, Python, dynamic, you know, scripting languages have this types of stuff here. So that's kind of cool here. Okay, and we'll get into lists themselves here. Let's keep that open in a page in case we have some time here. I think that's what we want to look at in these functional languages. But let's just start with here. 1, 2, 3. Okay, so semicolon terminated list. That's why we got the double semicolons at the end here. And yeah, we've got a list here. And here's that type deduction or type inference. Let's give it the correct term. It's telling us we got a list here. That's our value. So very clear here. And I wonder what the introspection capabilities are if I can actually print these out at any time, because this is kind of cool here. I like this. Okay, and then here's another string list. Let's just do, well, they're not binding it to anything here. Now, can I rebind stuff? Let's just play around with this. Can I make this now 2, 3, 4, 5, 6? 2 semicolons. No, false. Okay, I guess this is evaluating it. Yeah, we'll have to see how we do assignment then. I mean, this is kind of a functional thing then. If I let you, and very mathematical, like it said, it's sort of origins. Where was that on the help page here, or its roots here? Strong ties. What was it? Mathematical roots is what I was looking for. Yeah, so that sort of makes sense here. Okay, let's kind of keep moving along here. So this can be empty, the nil list, yep. So you see that some programming languages have adopted that. Maybe these are from folks who liked functional programming or maybe came from OCaml backgrounds where you'll see nil. Sometimes we'll see none. If you're a C-based language, you see null. So all these different things here. Let's see, most primitive operation is appending. Okay, new element. Okay, well, let's see how we do that here. 9, and then the cons operator. Yeah, so this is coming from like Lisp and stuff here. Okay. Let's construct a new list here. Let's do 9. You here, and there we go. It is appended here. Yeah, very nice here. Let's put in 10 as well, just kind of playing around with this. The spacing doesn't matter so much. Now this is kind of interesting, again, because, well, when I'm constructing this list, I'm returning a new one here. So if I run this operation again, right, this isn't like in a prepend operation if you're coming from like Python here, okay? This is the newly constructed list. So I think I need to bind that to another variable if I want to, generate list2 or something. Okay, sure, we'll learn about that. Let's look at our if then else. 2 times if hello. Oh, interesting here. Let's see. Equals world. Then 3 else 5. Oh, syntax error. How do I go back? Control P, Control N. Oh, nope, that's not it. Up arrow. Okay. 2 times if, let's see what we're doing here. If hello equals world. Then. Okay, and that's nice in the REPL that I can go backwards. Okay, up we got 10. So, I mean, this is already interesting stuff. This is the kind of stuff I imagine if you're used to coming from OCaml and you try to do this in other languages, you're like, why do we have to store state everywhere? Because I'm just, I'm taking the result of this here and saying, I'm returning this value and then getting 2 times whatever, the result of this condition is. That's kind of cool. I mean, I guess we could do this types of stuff with like ternary assignments in C and so on when you're like assigning a value. But that's just kind of neat to see 2 times if, and then you kind of say, okay, what is my returning value here? Yeah, ternary conditioner, if then else. Okay. Okay, values can be given names using the let keyword. This is called a binding value for a name. Yep, we'll try to use the right terms here. It's a value. Let's see, and bindings in OCaml are immutable. Okay, so we can't change them. That's why when we're getting that, let's see, when we're constructing here with the cons operation, that's just the list that's returned, but we're not actually changing with anything, right? Or it's not prepending to that particular list here. Okay, so although x is often called a variable, it is not the case. In fact, it's a constant. Yeah, these are like enums in some other languages. Think of them in that way. Let's see, oversimplifying but acceptable words. All variables are immutable in OCaml. Yep, okay. And that's the default that some new languages have been taking. Maybe we'll look at some other languages like Swift and so on and see some of the influence. I think that might be an interesting one to also look at. Okay, now in OCaml, it's possible to give names to values that can be updated with reference, and will be discussed in the working with mutable state. Yeah, let's go ahead and just take a quick peek. Whoa, that's way down here. Working with mutable state. Yeah, with ref, I guess we make references here. Let r equal ref, and then the value we bind to. Interesting. Okay, so we'll get there. We'll try to get there in this hour or so. Oops, let's get back to our here. Let me close out some of these tabs here so I don't get lost too much here. Oh, whoa, what happened? Okay. Let's scroll up here a little bit. Okay, here we are. Okay, so yeah, that was our mutable state. There's no overloading. Okay, so inside a lexical scope, names have a single value, which only depends on its definition. Yeah, these are the types of things that, again, if you have a strong type system, it makes it a little bit easier to have make it strong if you're sort of limiting yourself as far as what state changes can take place. And this is where, object-oriented languages, although OCaml is multi-paradigm, often struggle because you have a lot of different state that's contained per object, and that can be changing, right? So that's why some folks, talk about some of the inefficiencies or why it might be harder to write safe code if you don't have good defaults and so on. Okay, so some names, don't use dashes, use underscores. Okay, that's pretty standard in most languages. Okay, and let's go ahead and continue on here. Okay, so setting up variables here. And again, let's see what the error is that it's giving us here. Let y equal 50. Let's see some errors here. In y times y. Okay, now this seems to be working, but if I say y here and saying, okay, unbound here. Okay, so this is just locally defining the name here. Now that's kind of interesting, right? It's just saying in this particular expression, right? Because we're talking about scopes here. And then if I want to actually use it, right? So the scope of this is just this little chunk of code here. That's pretty neat here. Let a equal 1 in, let b equal 1. Okay, let's go ahead and see a equals 1 in, and that continues on, let b equal 2 in. Okay, so we're able to write more interesting expressions here. And if I just say a, right, unbound here, right? So it's just this context here. Okay, pretty clean here. And again, this reminds me of like a math course, right? For this particular proof, this is what we're showing here, okay? Okay. In OCaml, the equality symbol has two meanings. It's used for definitions and equality. Okay, so single equal sign for equality testing. And this is going to return a bool back because it's evaluating this condition, sort of right to left here as we do the assignment to this dummy value here. Okay, OCaml also has a double equal operator, which stands for the physical identity, but it's not used in this tutorial. Okay, interesting. And then we have negation here. Of equals. Oh, interesting. Okay, so we'll have to see how these operators are used differently. Well, we'll see how far we get here. All right, functions. We're doing a functional programming language. We should probably write some functions. Let's square x equals x times x. Let's call square of 9. And we get it here. So cool. Yeah, functions, pretty easy to write. Simple as that here. I like the conciseness here. This is one thing to really like about these functional languages here. Now, what's kind of interesting here, though, since I'm defining this function here, let's see what the value is that's produced here, or the type, I should say, right? We have an int that's producing some other int here, okay? And it's a function type here. No return keyword in OCaml. Its function body is the expression x times x. Let's see if, there's no sense of return, but sometimes I've seen in languages, it's just like the last value that you have here, which kind of encourages you to write small functions, right? You have to keep track of this stuff. Let's see if that's true for OCaml here. Okay, function. Okay, yeah, let's see what the REPL is indicating here. So I get square is int. This means it's a function taking int as a parameter as input and return int as a result output. function value can't be displayed, which is why fun is printed instead. Yeah, there's no, I guess, value here, but here's the type here. Okay, anonymous functions do not have a name and they're defined within the fun keyword. Okay, let's do the same. X, fun. The anonymous functions sometimes go by, lambda and other programming languages. Yeah, this is kind of cool here. So here's an anonymous function, immediately apply them to a value. Cool. So let's do that. Here's our anonymous function, and it's going to be applied to, well, again, no parens here, which is probably the clean thing to do. 50. Okay, so that's the argument for this function x, and it produces x times x here. Okay, and this produces int here. Let's bind this to something. U again. Okay, and if I just do u, there it is. Okay, so we're kind of combining some stuff here. I mean, this is pretty clean and clever, right? We're cruising through this tutorial here. Hopefully you're, if you'd like to follow along, or maybe at this point you've left and are just watching at this point. Let's see, functions with multiple arguments in partial application. Okay, so function may take several arguments separated by spaces. Okay, again, something to get used to, right? For those of us who like parentheses and commas, I actually like this with the type inference. Makes it very, very concise to write here. Okay, so let's cat AB equals A, and a space, B, cat for concatenate, I'm assuming. And let's go ahead and concatenate two things like cat and dog. And we get the string cat dog here. Okay, pretty clean here. No commas, no parentheses. We'll have to see what this looks like in a larger code base perhaps, but as far as just prototyping things on the REPL, this is really neat here. Okay, getting into some interesting stuff here. Let's see here. Let cat. Functions don't have to be called with all the arguments. Okay, this is kind of neat here. Okay, yeah, let's. And this is where the composability of functions matters in functional programming languages. Okay, so let's take our cat here and just say hello. I'm going to change this example up in a little bit because I think I understand it. I'm just going to call it like partial or something. So, this is a string that takes in one string for a function here, right? As opposed to our previous one, right? Where we can observe we're taking in two strings here. So now if I call partial on world here, okay, it's making use of our concatenate function. And we've sort of just captured a part of this function here. Okay, so I do get hello world there. Yep, again, neat, different way of thinking about things. Again, if you've never seen this in functional languages, but I'm enjoying OCaml. And it's been a long time, as you'll hear me say in this series, since I've tried these languages, but it's quite nice. All right, let's get into some higher order function stuff. And let's look at map here, getting exciting here. List.map, okay. Okay, so this tells me what it does here. It takes A and B and takes in a list and applies A to the list and B to everything in the list here. Okay, very nice stuff. Again, I've always learned these things from sort of a C or C++ background. I think what is in C++ has like transform, and Dlang you have map. They named it properly. So let's create a function here. So list map, anonymous function that'll be applied here. Let's go take function. We're working with our square here, x times x. Okay, and then we want to map this here. Okay, let's keep building on this here. I guess it's just gonna, this is the argument here, right? This is what we're applying to some collection here. Yeah, 0. Let's do our squares. Very neat here. Okay, so then we get all of our square root, squared values here. For folks who have done things like in Python with list comprehensions, again, this might be familiar perhaps. So again, this is pretty clean here. Okay, let's keep going here. Let's see, side effects in the unit type. Oh, interesting. Performing operating system level input operation is done using functions. Okay, let's do something here. I got read line. Now look at that, it's showing up in my help here. I want to see something. How do I get help here? I want to like select something. I can't click on it. But it is giving me the complete. If I do read line and then tab, okay, it is auto completing. That's kind of cool. And interesting. Okay, now I see a parentheses here. Okay, let's do that. Hello, friends. Hopefully you're enjoying this series. If you've made it to the 30-minute mark, let me know. Okay, read it in and stored the value. Okay, print end line. Let's see what that does. Print end line. Okay, it's a function. Unit function here. Okay, side effects in the unit type. Performing operating system level input-output operations does using functions. Okay, let's read about this unit thing here. Let's do print end line. And hello, my friends. Okay, we get our unit here. Okay, read line reads in some characters. End line prints a string on standard output, followed with the end line. Okay, so it gets us a little space here. Okay, they don't need any data to proceed. Indicating this absence of data is a unit type, which appears in their signature. Unit has a single value. The parentheses pronounce unit. Okay, let's pronounce that correctly. So read line with the unit. Okay, some tokens passed in. Unit types always used to indicate the presence of side effects, although not always the case. Okay, interesting. So let's keep moving along here. Uninteresting, I mean, you've seen me do some of these different impressions. I mean, hopefully you're subscribed and been watching, but I mean, we've been writing a lot of code here in the REPL already. You know, whether that's interesting or not, I think it speaks something to the language to say that I was able to just dive in and, you know, once I figured out this UTOP thing here, just start writing some code and learning. I think that's really a nice thing of a programming language, right? Versus having to set up like huge IDEs or something. So well done, OCaml, on, you know, getting this kind of stuff set up here. Okay, so let's see what we've got here. Recursive functions that can call its own body. Okay, and we need to use that rec keyword here. Okay, there are loops and so on in OCaml, so very good. Let's go ahead and try to write a recursive function here. Let's see what this is going to do here. Okay, if low is greater than high, then produce an empty list, else low, colon. Okay, what's this going to do here? We're going to, well, this is our cons operator here. Taking this range function, low plus 1, high, okay. Range 2, 5, interesting. Okay, let's see what we did here. Start with this recursive function for creating a range here. Here's our range, the low number and the high number. If low is greater than high, then just return the empty list here, okay? Because we've done something invalid. Like if I put in from 5 to 2, that doesn't grow, okay, effectively. Otherwise, we take low and we, whatever our low value was, so 2 in this case, right, where I did range of 2, cons it with, well, we do a recursive function call here with, well, this will pass in our range of 3 to high. And again, we're just constructing this, right? This is the recursive call. Okay, up until high here, okay? And this terminates, again, in our base case because, well, you know, this value is growing by 1 here, okay? So again, let's show it here a little bit higher. Let's try it with something like 5, 2, right? Gives us an empty list. And 1 and 100. Let's go a little bit wild here. All right, so very nice here. Nice recursive function there. Okay, data typing. So I am going to go through some of these things a little bit faster. I want to look at some of the advanced stuff. But hopefully that gives you a good preview of just what the language has as far as, again, as I mentioned, very concise, very easy to get into. Okay, type conversion, inference rules, lists. Okay, so a bunch of the list rules, probably important. You can have lists of lists, looks reasonable. Yeah, that's going to generate some list type. Okay, seems reasonable here. Now, can I mix things here? Again, let's just play around with let u equal hello, and try not to make a mistake, semicolon 1, and then we're going to have a list of 1, 2, 3, 4, and let's see, I guess we got to terminate this. Let's see, this expression has type int, but expression was expected of type string. Okay, so I guess we can't do that. Now, what if I put this in its own list here? Is string considered its own list? This expression has a type a list, but an expression was expected of type string. Okay, so those look like I can just mix and match things here. It's probably a different type here. Anyways. Okay, here's a recursive function that computes a length of a list here. That seems like a classic like homework problem or something. Let's do this one here. Again, going through it a little bit faster. Let rec, and this recursive function, length of u. Okay, so gonna match u with, okay, so now we're getting into some pattern matching stuff here. Okay, if it's 0, okay, if the length of our, let's see, I'm creating this recursive function that computes the length of our input here, our first argument, our first parameter, which is some list, and it says, okay, if I just pass in the empty list, then just return 0. Fair enough. Okay. For any other case here, I believe, you know, or the default pattern to check here, I want to do, let's see, v. Okay, so variable 1 plus the length. Okay, so just recursively calling this and incrementing by 1. Okay, that'll do it. Let's do the length of 1, 2, and 3. We get 3. Let's do the length of the empty list. We get 0. Okay, simple enough. But, you know, showing off some of the... and of course, the list of an empty list, right? An empty list is one element, so you get 1 here. Okay. Yeah, classic things. This is a good homework assignment or something to write here. And I guess it's polymorphic because it's just going to operate on any sort of thing, right? It's going to infer the type here in probably behind the scenes. I'd be interested at the actual code generation of this stuff, what it looks like. You know, for these functional languages. I mean, you get very simple functions, but again, you got to be able to, per type that you find, again, generate a version of this function that operates on it, right? So you can generate the assembly that, you know, fits enough bytes for whatever that type is. Yeah, very cool. Okay, so I'm going to go through this a little bit faster here, but we got to see some of the pattern matching. That's what I wanted to get to here. You know, rather than you just seeing me type out code, we can, you know, see some of these features here. And in fact, we're almost halfway through. We probably could have done this in an hour. But we've got higher order functions here. Oh, the pattern matching continued. Okay, this is getting into powerful stuff here, which is kind of cool. So if I got the none type, okay, so we're matching the operation here, or option, okay, of type option. If it's a none type, return none. If I've got, okay, let's actually read this. Never mind, we gotta read this one. Okay, it is a match with the first pattern. If opt is the sum none option, oh, I see. So, you know, a partial match or something. Let's see here. Yeah, this is the stuff I remember getting confused on 10 plus years ago. Okay, match the second pattern. Okay, double wrapped option. Okay, I got the sum with something else here. I mean, this is pretty cool, right? Just kind of, well, let's take a look at this here. Okay, pattern matching isn't limited to lists. Any kind of data can be inspected using it, except functions. Okay, fair enough. I wonder if you wanted to match different function signatures, though. There must be a way to do something. Patterns are expressions that are compared to an inspected value. If it could be performed using if then else, but pattern matching is more convenient. Yeah, I agree. I like this here. I think we're seeing some stuff, again, in other languages, you know, multi-paradigm languages like C++, they're always thinking about some sort of pattern matching type thing you can do. And folks have libraries, of course, in pretty much every language for these features. Here's an example using the option data type. Okay, yeah, we haven't learned about this yet. Fair enough. Okay, expected value is opt of type option compared against different patterns, top to bottom. Right, so it's finding the best match, and then we do some code here. Okay, fair enough here. Okay, let's take a look at this here. Yeah, and this is comparing the if then else versus pattern matching. I do buy that this is more convenient and clean. So I like this in languages if we are able to get it. Okay, here in G prime, if you will, you'll see this in names of things in functional languages. Match X with, you know, these conditions. So it's kind of like you know, again, if you're thinking in C, like I have to do like a switch statement, but much more powerful because you can match on like types or partial matches or some of these interesting things here. Okay, and here's like the catch-all case. Yeah, underscore symbol is catch-all pattern. Matches with anything. All right, great. OCaml throws a warning when pattern matching does not catch all cases. Okay, great. I mean, this is again the great thing about the type system in OCaml. If it's very powerful and you have a static type system like this, inferring all types, so you know all the information at compile time, you can say, warning, this function is going to execute on some type where we don't know what to do here. That's kind of nice here. Now, of course, I imagine if you have the catch-all case, it just, you know, tries to execute that. Alrighty, so we're nearing the end here. Let's keep looking at some stuff here. Pairs and tuples, very cool, as always. Yep, we need some pairs and tuples built in the language. Parentheses for tuples. Variant types, okay. Some languages actually just call this variant, but this is creating a type here that can be one of these things here. Again, these are like enum classes or something in C++, it looks like. So very cool. All right, here's a definition of a variant. Acting as a union type. Okay, so it could only be one of these things here. Oh, we're doing some HTML stuff. Cool. We got a string here. Okay, cool. We've got records. Okay, so this is like structs in C or something. I wonder if we can have member functions. We'll see, because there's object-oriented stuff here. They're probably not going to show you that right away in the tour here, right? They're showing you the cool functional stuff. Okay, yeah, makes sense. And you can have them named here for the actual record. Again, record's something I remember learning. I think in Pascal they have records instead of structs. I always thought that was a little bit of a better name. All right, dealing with errors. Okay, they handle exceptions, right? As I understood from the introduction, this is a garbage collected language. So that means that, you know, you try to catch an exception and then move on with your life if you can handle it at runtime. I wonder if there's assertions in this language. Perhaps the type system's strong enough that you never need to assert, so you can't have a failure. So that's kind of interesting here. Now they do have a failure like catch-all case at runtime, right? Their goal is not to crash or prove you can't crash, perhaps at compile time, as much as is feasible, right? Okay, let's see here. Using the result type, some function here. Okay, so again, these are some things, you know, I bet if I'd look closer at Rust, and maybe there's somebody screaming at me watching this, I think Rust does these kind of things too, which is kind of cool. So maybe some influence from the Rust folks on error handling here. So that's kind of cool. It almost gives me another, want to take a look at Rust again with a deep dive. Alrighty, mutable state, as we mentioned here. Ref, okay, let's do this one here. Let's add one more here. Let mutable equal ref 0. Oh, maybe that's is that a keyword? Mutable? Uh-oh, it is. Okay. I'll name it something else here. Let symbol. Okay. And then let's see. I can just do symbol. Can I reassign it like this? Is it that symbol? No. Okay. But it's an expression with an expected type of int ref. Okay, so what if I do ref in front of it? Okay, well, let's just follow the tutorial here. Reference is initialized. Oh, accessing the reference content is done with, oh, we dereference with exclamation mark. Hey, I like that. New syntax. Okay, so here's what we did originally. Here's what we did originally. Let's get this in a good state here. If I do symbol, okay, this gives us 0. And let's see here. Oh, okay, they do the assignment operator, like from Pascal. I like that. Symbol 55. And then let's, oh, we got unit. That's because there's something mutable as a return type. I wonder, you know, as far as tools that folks have, right? This is a good way to just follow mutation, right? And see where you have some error state. That's very clean here. Okay, let's dereference symbol and see if it mutated. It did. Brilliant. Okay. Simple enough here. And it makes it really clear by having a difference here with the assignment here that you can see where your state changes are, right? I can do a Control F and find all these things. So very cool. All right, so they got some library stuff. Okay, fold, map, join, bind, all sorts of things here. Very cool. So OCaml's got all the things here. All right, and I think we're going to make it to the conclusion here. I think this is the first time maybe through a tour we've made it through everything. I had to speed things up a little bit because I try to keep us under an hour. But they got the data types and matching, lists here, as I mentioned, full tutorial. I mean, look how well this is documented, right? So I'm never only just looking at the language. I want to look at the ecosystem as well. We've got built-in data structures, all the ones that we need here. Again, we can learn about the garbage collection. Ooh, meta-programming here. Okay. So I wonder what kind of introspection capabilities we have here. I mean, this is just cool stuff here. Yeah, very cool here. We're in the language. There's pointers. Okay. Oh, status of pointers. Okay, they exist. Interesting. Functors. Okay, stateful objects. Oh, interesting here. In these modules here. Okay, so there's all kind of cool stuff here. Let's just kind of look, you know, I wonder what's in this playground here. Oh, we could just run some code here. Blog, community, packages. I don't know, OpenGL or something. Cool. I mean, there's stuff for gaming and so on. So, well, let's go ahead and kind of wrap this up here. They got an active blog here. Cool stuff here. Very cool. They're building some different lock-free tools. Okay. I mean, again, with these sort of first impressions here, what I can say is I really like how concise functional programming languages are. And I like that a lot of other languages are borrowing these things, right? These nice sort of practices with mutability and safety and pattern matching to make our code more expressive and readable. I mean, these are all just really cool things. I'd be curious to do more of a deep dive maybe with some of these languages, for instance, to see like, what does a project look like that's 10,000 lines of code? What do they, you know, how do they organize them? That might be a next step for you if you've enjoyed this and, you know, if this is your first exposure to OCaml. If you've seen OCaml a bunch of times, you're probably yelling at me to show something cool. But please do post that in the comments if you did find something. Again, I think this is a really nice language, OCaml. Again, I have used it. I've used ML previously, you know, which is this has origins from or roots in. I'm impressed with the ecosystem, the tools. I mean, what I'd be interested in is to learn more about the compilers, some of the code generation. If there are things, you know, like Android applications or weird stuff, you know, outside of the realm of what we're finding here that are being built, I think that'd be cool. So I'd love to learn more about that. All right, folks. So with that said, that was our first impression of OCaml. Again, I love learning all this stuff. Hopefully you're enjoying this series. Make sure you subscribe so you can see all the languages that I get to explore. And again, if you're an expert in one of these tools, let us know in the community. We'd love to know the next resources to take a look at, what exercises you'd recommend for beginners learning this language, or maybe just programming in this language. That would be great. Anyways, folks, with that said, thanks for your time and attention here today with OCaml, and we'll look forward to seeing you in the next one.